but this only happens once, so you kind of front-loaded ghost. And how you use this dispatch tab? So here we have our block, right? Here we have some state that this will be the state of our recompiler, and here's our rough parsing loop. So we have some offset. This is where we are in the program, and we start at 0 because we start recompilation at the top, right? And while we are not at the end, we just fetch the opcode, right? Fetch it from the block. And then we have our dispatch table, so we index the dispatch table with the opcode, so we get a function pointer to the handler for the instruction, right? And we just call it. And then you go to the next instruction. So this is a very simple loop, and it's reasonably fast. And just a little anecdote as to why I'm also talking about parsing. Some time ago, in PVM, I have implemented module caching, right? So instead of recompiling the module every time we get a new program, right? It'd be nice to check if we already recompiled it and just reuse already recompiled program, right? So I implemented this, and to my surprise, it ended up being slower than recompiling the program from scratch every time. Like calculating the hash of the program was slower than just recompiling it from scratch anyway. So that's also why I'm talking about this whole parsing, because this is also important for performance. Even a single extra instruction is measurable here. So that's why it's nice to have like a very tight optimized loop for this. So let's implement some handlers for some of the instructions. And so first thing you want to do is you want to decode your instruction, right? So if you remember, our instruction had like 3 operands, right? 3 registers. So here we read the register, right? Read from the block, and then we translated the register of our guest. So R0, R1, R2, or R4, we want to translate those into a native register. So the register that our CPU uses, right? And we do this for every operand, right? So once we parse the instruction, we immediately emit the machine code, and this is some like I mean, this is kind of pseudo, right? But this is going to be some dynamic assembler that can emit machine code at runtime, right? So this is like an example for like AMD 64x86, right? Where you go to recompile and add instruction. So in AMD 86, I mean, this is a 3 operand instruction, but in AMD 86, the operands have 2 instructions, and they are of this form, right? It's destination plus equals source, right? So you cannot recompile this like directly. You need to like branch and see like if the destination matches source 1, then we can just do like this, right? If the destination matches source 2, then we can do like this. And if all 3 registers are different, then you need to emit 2 instructions, right? First you need to move the source 1 to destination, and then you can add it. So essentially, this is the whole code generation thing you need for running a recompiler. I mean, it's not, as you can see, it's not very complex. And essentially, the whole PVM was designed so that you don't need like a crazy optimizing recompiler. It was designed so you can do this essentially. Just parse the program block and immediately emit machine code. And you don't have to do any special jailing or anything like this, or anything more complex. So here we have this 2 native records function, right? So we want to assign the registers for guest machine to the register for the host. So the question is how to assign them, right? So in this case, our guest machine has like 4 registers. In PVM, you have 13, right? And on AMD64 we have like 16 registers available, general purpose registers, and we want to statically assign every guest register to a native register. So essentially you just hard code this. This is usually in like conventional recompilers for like QM or something. This is like done semi-dynamically, right? The PVM was designed so that you can do this, so that you can hard code this, and the recompiler, the VM doesn't have to shuffle things between registers and not splitting into memory. So for example, we can assign R0 to RD and so on. I mean, so yes.
I wonder, like, what about Apple Silicon? Like, is it also matching like the register?
Yes, on Apple Silicon it should be easier to write the compiler. Yes, because there are more registers and the instruction set is not fucked. So, like, AMD64 encoding is crazy and the instruction set is crazy. So this is the hardware version. But the toaster runs on AMD64, so I mean you can write a compiler for Apple Silicon, but it's not gonna run on toaster then. So yeah, we won't be able to measure the performance. But as like a side project or something later, you can certainly add one, and it should be easier because the instruction set ARM is a lot more sane. Anyway, so which registers to pick, right? Because we have like 60 native registers, and like in case of PVM we have 13. So, and I'm not gonna delve too deep into this to not be too technical, but I mean, spoiler alert, you can just do something like this. So for the guest registers, just use these. As a temporary register for the recompiler, you can use this one. Essentially, why do you need a temporary register? Because some instructions cannot be recompiled one-to-one, and sometimes you need to shuffle the data around, right? So you need at least like 1 or 2 registers to be able to like do this shuffling, right? And you want to pick something like RCX because some instructions on AMD64 have hard-coded registers. So it's not like you can, so you cannot choose your own register. They just use always the same one, and a lot of the instructions use RCX. So we just pick RCX so that it matches with those instructions. So in those cases, we don't have to shuffle manually around because the instruction already uses the register we want, right? Camera. And you need at least 1 register for to hold the virtual machine state. So things like gas or like exchanging the registers with the host, you will use this as a pointer to a structure where you will write those things, right? And this stack pointer you just should probably leave alone. I mean, you can use it, but it's more pain, not worth it. Yeah, so this is our other instruction, so the finish instruction, the one that just like stops. So we just emit a return call. So now we have Recompiler program, but now we have to run it, right? And how do you do that, right? So we need to use an mmap code. Mmap is your friend. I can recommend that if you have a Mac OS or Linux machine, you can type in man mmap and you get a manual and you can read what mmap is and how to use it. But in a gist, mmap essentially allocates address space and memory. It's just like a very low-level system call to request memory from your operating system, right? And I can go through the parameters. So first parameter, ignore this. You want to put null in here. The second parameter essentially specifies how much memory or how much address space you want. So in this case, like we want as much memory as we have the bytes of our machine code, right? Here you specify the protection flags, so you want it to be readable and writable because we need to write the machine code, right? And here we specify that it's anonymous, so it's not associated with a file descriptor, and that it's private, so we will not be sharing it with other processes. And the next two arguments, you just ignore them and hard code those things. Yeah.
Excuse me, could you repeat what that
Yeah.
FD fund?
Which one?
Was it? FD. FD? Funding descriptor? The FD term?
FD?
Yeah.
That's a file descriptor because like this mmap function can be used for multiple things. It's like a very multi-purpose thing for mapping things into memory. And it can do things like, for example, map files into memory. The same system call. So FD is like a file descriptor, so it's essentially a file handle, right? So what this can also do is you could also open a file, right? And then you remove this anonymous flag, and then you stick the file descriptor here, and it will put the file in memory, like map it, right? That's what I mean by file descriptor. So this flag essentially does that. We are not giving it any file descriptor because we don't want it to map a file, we want it to allocate memory, like anonymous memory. That's why this flag is called anonymous, right? Yes. So, any more questions? Okay, so that's how you allocate memory for your code, right? And then what you need to do, you just need to copy your code into that region, or if you want to optimize things, you could like pre-allocate this before you recompile and then directly copy, directly edit it into the already mapped region. Just skip the copy to build faster. You can do this. So after you copy your machine code, right? And this is just a normal Rust memory copy. This is just mem copy, and if you're familiar with C. Then you want to call mprotect, and what mprotect does is that it essentially changes the access flags on the memory you've allocated, because this is executable code, so we want to run it, right? So we change the permissions on the code to be readable and to be executable, right? So you might notice we removed the writable flag. We do not want the machine code to be writable and executable at the same time. This is a horrible idea for security. That's why we didn't put prod exec here. We don't want to make this immediately executable because that's the way you get hacked, right? Yes.
Does the process doing that need some elevated privileges? Or?
No. I mean, depending on the OS. On normal OSs, you don't. Sure. On normal OSs, you don't. If you're using a shitty OS like iOS, then you cannot. Only Apple can do this on iOS because they don't trust you to be responsible.
So there is no way to write a compiler to Apple Silicon if you are not running Linux.
No, like on macOS it works.
Oh, macOS works.
On iOS it just doesn't work because like Apple doesn't like you. Yeah. Yeah, so like once you do this, right, it makes it readable and executable. It's runnable, and then you can jump into it. But before we can jump to it, we need to store the guest register somewhere, right? So what you want to do is you want to make like a VM context struct, and in this struct you will put all kinds of crap that you will need for your VM, like registers, like gas, and a bunch of other stuff. So everything you want to be accessible by the guest and by the VM, you just put it here, right? So here we and normally you would allocate it on the heap, and you would probably put a pointer to it in thread local storage to be able to access it anywhere. You essentially want it to be like somewhat global. So this is a program, right? It calculates R0 equals R1 times 2 plus R2. So here we can set the initial values of our register. So the inputs, we just set it in this struct we just defined, right? We just set the inputs of our registers, and then we can call it, and this is a little bit of a higher stuff. So this is like inline assembly. That's why I was saying that. I mean, you could technically do this in Python by emitting raw machine code and executing it, but like it's easier to do with inline assembly, right? So bear with me as I try to explain this. So this is essentially an inline assembly snippet, right? And you don't write normal assembly code, but inline assembly has some differences. If normal assembly, like as a separate file, and inline assembly is different because with inline assembly, this is embedded into an already existing code. So you need to tell the compiler which registers you are using and how you are using them. So this crap down here, like in, late out, in, this essentially tells the compiler which registers you're using and what you're using with them, right? What you are doing with them. So for example, I specify late out for racks, right? So this tells the compiler that I will be clobbering this register, which means I will write some value in there. So this tells the compiler that it should make sure to save this register before calling my inline assembly. So somewhere here it will save it, and then somewhere here it will restore it automatically. So you need to get this right, or else you will have a very fun debugging session that will last a long time, and you won't know what's wrong, right? So you need to make sure you actually specify everything. So here, here we have our code pointer, right? So this is where we copied our recompiled code, and we pass it into the RCX register, and then we say to the compiler that, hey, so we are passing something in this register, and laid out means that we're essentially clobbering it. So please restore the original RCX after this inline assembly ends. That's what this laid out means, right? Then we just say that, hey, we're going to be clobbering we're going to be dirting the RAX register, some other registers, and R15. So this asks the compiler to restore it, but we don't need any value passed in here. Yeah, and then we say that in R15 we will be passing a pointer to our virtual machine context, but this register will be unchanged by us, so we just pass only in, right? So the compiler doesn't have to restore it, because at the start and at the end of this snippet, it will still be equal to this. We were not changing it, right? So now to explain this code a little bit. So we manually push some registers, but what do we need to do this? Why didn't we just do laid out with these registers? And that's a compiler limitation, because you cannot actually use every registers. If you use RBP or RBX here, the compiler will yell at you and say that that's not supported. So you need to do this manually. So essentially, this is exactly what the compiler is doing with this. It's just that it's doing it automatically, right? But for those two registers, you need to do this manually. And then here we are loading all of the guest registers, right? So R15 is our pointer to our virtual context, right? And it has our guest registers. So just from the offset 0 at R15, we copy the R0, right? So this is this array, right? We're reading values from this array, and we are reading them into the native registers which we previously picked, statically, right? So we load all the registers, and then we just call the guest code. So this is R6, that was the code pointer, right? The pointer to our recompiled code. So we just call it, right? And this just uses a normal function call, and then this calls our code, and the code will return. And then here we read back the native registers and put it in that struct, so that we can read the registers, guest registers later after this thing finishes, right? So we read them back, we pop the save registers, and we're done. Yes?
Does that mean that the guest code could have changed the registers? Because we read that before. So are they going to be changed so that we have this one?
Yes, I mean, the guest can change those registers because at this point, those registers become guest registers, right? And the guest can change them. It can modify them. So after the guest finishes, we want to read them back to see what the guest changed, right? Everything clear? Or is something not understandable? Good. So here we can just read, like, we can read R0, right? And then that will bring out like 23 because this is what the program was doing. So here we have a basic recompiler, but of course we're not done yet. There's still a lot of moving parts. So sandboxing memory, I mean, this was just like a simple instruction set. It couldn't access any memory, but in a real instruction set, you will have instruction access memories. Memory access instructions, sorry. You need to prevent the program from accessing your host memory and reading your bank details. So how do we do that? How do we prevent the guest from accessing host memory? And how do we catch guests' invalid memories? So for PVM, for inner VMs, you need to cache like page faults, right? You will use exactly the same mechanism to do calls. So first thing that we want to do to sandbox memory is we want to reserve some address space. So here we have our friend Emma, and we also use this for reserving guests' memory, right? So first argument, as previously, we'll leave it at null, ignore it. Then we specify how big of an address space we want, and here that's 4 gigabytes, right? 4 gigabytes and a little bit for protection as a guard page. So as you might remember, in PVM, the address space is like 32-bit, right? So if you have a pointer in PVM, it's 64-bit, but the upper 32 bits are ignored, right? So essentially what we do here is we want to allocate as much address space as we can to match exactly how much memory in theory can a pointer access, right? So since only the lower 32 bits are used in PVM, we want to allocate 4 gigabytes of address space. And as you can see here, here you would normally put the protection bits, so like prod read, prod write, something like that, right? But here we put 0, and what this means is that this memory region will be unreadable and unwritable. So essentially, it would act as if you wouldn't even allocate it. Like if something accesses anything in this memory region, it will just crash. For now, right? And this is the same as before. It's anonymous and private, right? So this allocates 4 gigabytes of memory. Not really, it just allocates address space. This doesn't actually allocate memory per se, just address space. And we probably actually want to allocate some memory in this address space. So memory that the guest will actually be able to access, right? So let's say this is the address of the memory that we want the guest to be able to access. And this is the length, so it's like 1 page at address 64K, right? So here we use our friend mprotect. So this is the base pointer to the guest memory, and we add the address. So this is the address that will be used within the guest memory, right? And we set it to guest length, and here we set the access of this chunk of memory to read and write. So this makes it accessible, so that the guest now will be able to read and write to it without crashing. So how do we let the guest access this memory? I mean, in our inline assembly snippet, right? We can just pass this guest pointer in one of the registers, right? So in this example, it's like in R14. And yeah. So let's say we have like an instruction that's like this, right? In R1 we have a pointer to a 64-bit value, and we want to read from this pointer, we want to read value into R0. So this is how it can be recompiled. Like here in Rax we have our pointer. This is guest code. This is recompiled code, right? This is what you will emit from your memory access instructions. So here we have Rax is 64-bit, right? But we want to ignore the upper bits. So what do? We can move it into a 32-bit registers, and by moving it into a 32-bit register, the upper bits will get cleared. So now they are 0, right? So now this is our offset, and then R14 contains the pointer to the base of our memory, our guest memory, right? So we just add those two together and read this cell from memory into a register. So hopefully this is pretty clear. Yes, essentially the PVM was designed to make something like this possible, so you don't have to do branches or anything. You just mask the upper bits, right? And you can just read the guest memory. Yes.
Right. And if you access it outside, let's say, because now we reserve like a little, one page of memory, and if we would go inside the M-mapped space, we would go outside of that little page, then the system would crash, or can we catch that?
Yeah. You mean, because here the guest can only access its own address space because we allocated for 4 whole gigs those one page.
Yeah.
So it's impossible for it to access anything else in it. But if this tries to read a region of memory that wasn't like here we said it read and write, right?
Exactly.
But only a chunk of it. So
exactly.
if it tries to access outside of it, yes, that will still crash our program.
Exactly. And can we catch that?
Yes, that's what.
The next slide.
That's the next slide.
Okay, sorry.
No way. So yeah, but we still need some way to kind of see that memory access, right? Because if the guest reads or writes somewhere where there's nothing allocated, then that will crash our whole thing. So what we're going to do is to set a signal handler. And what is a signal handler? Essentially, it's like it's a callback that the operating system calls when something happens, usually something bad. And so in this case, we want a segmentation fault signal handler. And essentially, a segmentation fault is that the program accessed memory which wasn't actually accessible. That's when you get seg faults. If you have some experience with writing C or C++, you should be very familiar with seg faults. Anyway, so what you want to do is, this is applicable to macOS and Linux. You can also do this stuff on Windows, but you're on your own, so good luck, but it's also possible. Anyway, so you want to use essentially sig action to subscribe to this signal handler, right? I'm not going to be explaining what this is. You can read the manual. For all of those low-level calls, you can just type man, name of the call in your terminal, and you'll get a manual, and you can read in detail what it does, right? So essentially, you register this function as your callback, and every time the guest will access the memory it shouldn't, it always will call this for you. So how do you handle this? And in this signal handler, you have access to the whole state of the guest. You have this info, and you have this micro CTX parameters, and those contain all of the juicy stuff that you can use. So micro CTX contains all of the registers, right? So you can grab every register, every guest register. You can actually grab the exact values at the time of the crash, and you can also page fault, I guess. You can also figure out where exactly in your recompiled code this happened. So this gives you the address of the native code, right? This doesn't give you the address of like the PVM code, but you can easily translate it by like, when recompiling, you can build, for example, like a sorted list and then binary search into it based on this address to find the PVM address of the code that triggered the page fault, right? So that's relatively easy. And you can also grab the address that the code tried to read. So based on this, you can figure out which page it was. So for example, for inner PVM, you will then use this value to return to the outer PVM. Yeah, and so you grab whatever you need to grab, and then you can jump back to the host code. So how do you jump back to the host code, right? This gets a little bit more complicated now. Because you cannot just return from the signal handler. It will just go back executing the same code that crashed and will crash again. So you need to, I mean, there are multiple ways to do it. One way is something like this. This is our inline assembly snippet that we use to call into the guest code, right? So we can do a little bit of setup to make it possible to return from the signal handler. So here we have some usual setup, and this is our call into the guest code. And after we call to our guest code, we put a label. This is just normal assembly label. So what we can do, we can load the address of this label, because once our signal handler returns, we want to return here, right? So we load the address of this label. We chuck the address into our VMCPX struct. So the struct where you put all the crap that your VM needs. We save the stack pointer, and then we jump to our recompiled code. So now our signal handler has enough information to be able to jump back here out of this signal handler, right? And here we have the handler, right? So we can read this stack pointer. So restore the stack pointer and jump back into out of the execution of the guest, right? Something like this. I mean, there are multiple ways to do this. This is just one way. Yeah. So this is your basic VM that it is sandboxed and yeah. Yes.
I have a question there, because you used call, and now you use jump, right?
Yes. I mean, because you probably want to jump, I mean, I used call to simplify before, but in production code, you probably would want to always store every register, and then use jump because the difference between jump and call is that jump just jumps and does nothing else, and call saves the return address on the stack and jumps.
Okay.
But if you will be saving the return address in VMCPX, then you don't need the call. You don't need to store it on the stack.
Okay.
So the call is pointless.
Yeah.
So that's why this is changing to jump, because the address now is in VMCPX, so we don't need to store it on stack.
Okay.
Yeah.
One more question.
Yes.
So the assumption is that this zigzag handler will be called from the same thread as your main thread, right?
Yes. This all needs to be run on the same thread.
Yeah. Okay. I mean, I guess you just have one thread going on in your program, and then you know which one it is.
You mean the VMCPX? How do you know from
I
which?
was just wondering because I guess it's dependent on the operating system that it always picks this thread. Otherwise, it's some kind of weird entry point where you also take.
Okay. I know what you mean. You're asking because this is a global handler, right? So you're asking which thread will handle this signal handler? Yes. So that's this call that we use the sig action. As far as I remember correctly, this is only per thread. Or if it's not, you can set up I don't remember exactly, but You can set up a signal handler per thread, so it will only fire for a given thread. So you want to set not like globally on this whole program, and then you don't know which thread will handle this signal handler. You want to set it on the thread where you execute the PVM code, and then only that handler will trigger on that thread. Yes. Yes, and this is also what I said, the VMCTX pointer, you probably want to put it in like thread local storage. So you should consult your programming language docs on how to do this, but in most languages you can do it in lower level languages. So this you want to chuck into like thread local storage, and then you can just access it from your signal handler. Yeah, so yeah, that's like the basic VM, which should be enough to get you started, but there are still some details that you need for an actual VM. For example, gas metering, right? How do we do gas metering? And this is seemingly simple. You just chuck in like a gas counter in your VMCTX, right? And then you can do basic gas metering. So this is like access your gas counter and subtract the gas. So gas minus the cost, right? And then if it became negative, so if we run out of gas, then just jump to your out of gas handler. Pretty simple, but as always this has some variations that you can do, because we need to figure out where we run out of gas exactly, right? At least for the inner VMs. Because you need to be able to continue after you return to the outer VM from the same place where you run out of gas, right? So you can't just blindly stop the execution, you need to know where you run out of gas. Like, because this just jumps somewhere, right? But if it jumps somewhere, then you don't know where the jump came from. So there are a few possibilities you can do. You could you could have, for each place you check the gas, you could have a dedicated handler, right? So then you know where it came from, because each gas checkpoint has its own handler, but that's kind of inefficient. Another option is you could just load the address of where you're coming from into your VMCTX and then jump. So then you know where you came from because you have it in your VMCT extract. Another option is, we're going into crazy territory now. You can have multiple handlers, but instead of writing a bunch of code to handle the out of gas, you just put an instruction which crashes your program. Essentially, it triggers your segfault handler, and then in your segfault handler you can figure out from which address you came from. And this saves you some instructions because you don't have to put like the whole handler here. You just put one instruction, and then handle the out of gas by crashing. And you have the most crazy option. Please bear with me. This really requires some explanation, but this is technically the most efficient. So here we have our gas counter, and it's at address 61, at offset 61 in our VMCT extract. And then we jump 5 bytes backwards. And what does this do? This is the raw disassembly of this instruction, right? Here we will have the gas cost. So those are some big X's because this will depend on the location. Like, this is how much gas we charge, right? And this is the MD64 encoding for this instruction, right? So what we do here is essentially we jump, let's say 5. So like 1, 2, 3, 4, 5. We'll jump here, and the instruction with opcode 61 will get executed. This is in the middle of the previous instruction, but so it happens that opcode 61 is the pop-up instruction, which is invalid in 64-bit code, which would crash our program. And in our signal handler, we'll get the exact address of where this happened. So we will know from where we ran out of gas, but we don't have to like explicitly store this anywhere, right?
That's nice.
Yeah, so Yeah.
Crazy.
So this is one of the one of advanced techniques you can use to extract more performance. Yes.
I believe we've had talks about like making it illegal to jump into the middle of a instruction.
I mean, in the guest code, it is illegal. You cannot.
Okay.
I mean, from within the program, you cannot.
Yes.
From outside, I believe it's still allowed in the gray paper, but it probably won't be so.
Okay.
To simplify things, yeah. But in native code, you can do stuff like that. So this is also why using native code directly, because I once was asked, why did we define our own bytecode? Why didn't we just like run x86 inside VM? This is why. So just some general tips on how to make it fast, right? Because this might not be obvious to everyone. So first, you don't want to allocate memory. If you need to allocate memory, just allocate it upfront and cache it. And when you recompile your program, you should have 0 allocations. So do not allocate anything. And if you're using like a garbage collector language, then you probably want to make sure you don't generate any trash and you disable your GC temporarily when you're recompiling. So just like a side note, if you're using one of the low-level languages like C++, right, you can write the whole recompiler in that. That should be fast enough. If you're using a language like Java or Go, you might be able to pull off a fast recompiler. I don't know. I haven't done it. It might be possible, but you will have to write some non-idiomatic code. Like for example here, you will have to be very, very careful to not allocate any excessive memory, right? So it might be doable. I don't know. If you want, you might try, but it would be simpler to just go to something lower level. You should probably also minimize some unnecessary abstractions. So as you saw with the example with parsing the code, we essentially parse the bytecode and immediately emit machine code. We don't go through any intermediate representations. We don't make it like nice. We just do the simplest thing possible, and that's usually what's the fastest, right? So you don't want to abstract things too much because it's just going to get extra overhead. This is like more of a, because like if you're going to be emitting AMD64 code, which is crazy, you probably want to use a library, but the problem with most of the libraries is they are actually quite slow. And as I said, even like a single extra instruction is measurable when you're recompiling code this fast. So ideally, you would probably want something faster, something that's actually written for like emitting code fast. So you can write your own, you can like use off-the-shelf library, but should probably benchmark it and see if it's fast. Or you can just use mine. I mean, this is not like part of the GP. This is just like normal general purpose assembler. It essentially supports every instruction you would need for a PVM. So you should, if you want, you can safely use this without any like collision, because this is just like the dynamic assembler library. Has absolutely nothing to do with GP. So if you don't want to write your own, feel free to use mine. Feel free to like translate it into your own language, and it should be fast enough. This is what I'm using, right? So yeah. Alternatively, you can just write raw machine code by hand. I've seen people do this. I wouldn't recommend it because for your own sanity, but if you're crazy, you can do it. And it's going to be fast, but it's not going to be pleasant. Yeah. So a few more tips, we're almost at the end. Efficient instruction decoding. So you might remember this was our instruction handler, right? And we do read some instruction, we do read the operands here. So we can actually make this faster by quite a lot. So what we can do, and PVM was designed with this in mind. with like these various tricks that you can do to speed it up. This might not be obvious, but like here, what we do is we have the program block, line and offset. So what we do, we just read 128 bits. So this will essentially be 2 memory reads. This will read 2 64-bit values into 2 registers. So this is very efficient, only 2 memory reads. And then with this 1 memory read, like if we can, we want to minimize the amount of memory reads we do, right? So if we can read more data, and just extract it later than we should. So here we read 128 bits, and here we extract the opcode with like some bit operations, right? And we dispatch into our handler, and we just pass this whole chunk that we read, right? And then instead of reading byte by byte from the blob directly, we just extract the arguments from this chunk that we read, and we just use like normal masking and bit shifts. And this is much faster than just reading it from memory byte by byte. It's a lot more efficient. And the whole thing was designed so that you can actually do this. So for the instructions to decode, every instruction you only need to read at most 2 64-bit values, and to decode the bit mask. So you know the 0-1 mask that tells you where the instruction starts and ends. You just need to read 4 bytes at each location. And so this is much faster, right? And another thing you can do, you will want to map guest registers to native registers, right? So you can do it naive way, or you can make like just like a lookup table. And in general, since this table is small, it will fit in like L1 cache. So this will be very, very fast because there are no branches here. In general, for fast code, you want to minimize ifs. You don't want ifs in fast code. You want branchless code. Yeah. So if you're wondering, these are like the equations for decoding the arguments from the GB. And if you're wondering, like, for example, why do we need like this mod 16 or like this might look weird, right? So the reason why this looks slightly weird is to allow tricks like that. So this is not explicitly spelled in GB, but that's the point of some of the weirdness. So you can use these low-level tricks to speed up your recompiler. Yeah, that's all. Hopefully it was understandable and I didn't bore you too much.
Questions?
Yes.
I think.
So you mentioned running it in one on a separate thread. Is it not on a separate process because you don't want same security as VM? Our guest program should not be running on the same settings.
Yes, I mean, so you're asking about sandboxing, and there are multiple ways you can do sandboxing. The way I've shown here is doing sandboxing within the same process. But there are other ways you can sandbox. You could technically run the code, the guest code in other process, and just communicate over shared memory, and that's like a more secure way of doing sandboxing, but it's also a lot more complicated. That's why I didn't show it, right? Like in PVM, I actually run the guest code in another process, sandboxed in a much secure way. But like that's like another 12 layers of complexity. So I just didn't want to put it here in the slide because it would just be too much. But yeah, there are multiple ways to do it. Yes.
Yeah, when you grab the big chunks, then do the bit shift and the masks. What if you grab more than what the instruction needs? You grab a big chunk and then you check the opcode bit mask, or?
I mean, for the loop here, yes. So this here, I mean, if you grab here, if you grab more than the instruction needs, it doesn't matter. I mean, those bits will just naturally get ignored. Like the instruction will just not use them, right? Because it will just bit shift whatever it needs and leave everything as there, and you leave everything alone, right? But there is one correct case here that you need to be aware of. I mean, if you're gonna read like 8 bytes here at the time, what happens at the end of the block, right? Because you don't want to read out of bounds. So this is a special case you need to handle like specially. So what you would probably do is you would maybe have 2 loops, right? And this loop will be guaranteed to be always within bounds, and then you will have like another like loop or something below that will do it the slow way. That will just read normally byte by byte and just pack it into manually pack it into U128 and call it dispatch table so that you don't read out of bounds. So you need to take into account these kind of correct cases. But since this will be only done for like a few bytes at the end of the program, it just for performance it just doesn't matter at all. It's just a little bit of extra complexity.
Can you align the blob size, or it's gonna be too slow because it's in one corner?
Can you?
Can you align the blob size to always have
I mean,
and the other one will be more.
I mean, you would have to like expand it, fill it with zeros at the end.
Make sure that.
In general, I mean, if you would do that, you would probably have to copy it, which you can, but like that's going to be a little bit slower. Like if you just like take the block unmodified and just parse it as that will be the fastest, right? Because you're not doing an extra copying. In general, you want to minimize the amount of data you copy. So if you can do it something in single pass without copying, you should do it. Right? Even if it's a little bit extra code to handle the corner case of like what happens at the boundary, which is annoying, but it's not that bad. Anything else? Yes.
Yeah, so how do you think we should be benchmarking our attempts to do this with things that you have done?
I mean, first things first, you should make it work. Then I would recommend trying to run Doom at full speed. If it runs at 60 FPS, then you should probably be good at least for the hot speed milestone. And then we will see. I mean, I do want to like make some generic benchmarking harness for everyone. So we'll see. I mean, ideally it would be cool to benchmark every PVM against everyone so that everyone's like motivated to clean the leaderboards of speed. So I think that would be cool to have. But yeah, just first make it work and then make it run Doom and then go from there. Yes.
Okay, sorry. How do you think we should standardize our PVM traces? Just wondering from your perspective.
Traces. What kind of traces?
You know, like here, you know, after each instruction, here is the state of the machine. However you want to describe the state of the machine.
Do you mean logging? I don't know. I mean, in general, like those kind of traces are like nice for like debugging, but for like, I mean. The problem with traces and the recompiler is that if you want to inject like this kind of tracing in the recompiler, this is extra complexity. You can do it, like I support it, but it's annoying because like before every instruction you need to inject extra code to call back into the host, so the host can actually do the tracing, right? So it's kind of annoying. You can do it, but it's more code. But as far as the exact format that you do, you just I don't think we actually need like a standard here. Like one thing that we will want to standardize is like we were talking yesterday, an execution trace that your VM would emit at the end, and only will have the I/O on the guest host I/O points. So that will allow us to reply the whole execution. So that's the kind of trace that we will want to like standardize across VMs. Like the exact execution state trace instruction by instruction, I don't think that's needed. Yes.
I think about the jump table, how it kind of like will fit or match the addresses of the jump table with the code that is being like parsed into like the. There will be some sort of also like a. I don't know if I have some general idea on that. I'd like to know more. How the
Which jump table do you mean? Do you mean the jump table in the PVM block?
Yeah,
For the dynamic jumps?
the dynamic jumps.
Yeah, so I didn't touch on that, but essentially how you would implement that is through indirect jump. You essentially do. So when you recompile your PVM block, for every possible dynamic jump you want to essentially write, you want to essentially build a table from the addresses you get in the PVM block to your native addresses. And then in your recompiled code, you put offsets into this table, and then you do indirect jumps where it will read the address from the table and jump into the PVM code. I mean, I'm not sure if I'm explaining it well, but it's not that complicated. You just essentially build a mapping from the jump table to the native address, and then just do the jump. Yes.
So that would require like going to the heap to check the jump table. Like you could do like 2 passes as well as inline.
I mean,
I wonder if you checked if this is faster to like second pass and then inline the jumps. Oh no, you can't inline. Sorry.
You cannot inline.
Because they might.
The dynamic jumps you like, because you have like 2 types of jumps in here, right? You have static jumps and you have dynamic jumps. And with static jumps, you know exactly where it goes. I mean, it always goes to the same place. So I mean, technically you do need like a second pass, but it's not a second pass in the sense of you going through the code. It's just a second pass of like you recompile your PVM code, right? And you encounter a jump, and it jumps somewhere, but it jumps somewhere forward. So you haven't recompiled this code yet. So what you do is you insert like a dummy jump. So like jump to nowhere, but just like allocate the space for the whole address. And then once you get down to the place where you're supposed to jump, now you know the address. So you can put it in like a vector or something. And then once you finish recompiling, you can go through this vector and fix up all of these addresses that have been filled out with the actual values, right? So that's how you handle the static jumps. And like the dynamic jumps are similar. It's just that you build your table like on the side, and then later you use this table for dynamically for like dynamic jumps, right? So it's kind of similar. So in a way, it's like multi-pass, but only so far as to fix up things which you couldn't immediately amend.
But sorry, one more follow-up question. Do you like kind of create a part of code that does the dynamic jump table, or rather do you inject the code that reads from the memory, like where they should jump and then we jump?
I mean, the dynamic jumps is just a single instruction, essentially. So you don't need any complicated code for those dynamic jumps. It can be done in a single instruction. I mean, as always, there are multiple ways to implement this, right? So don't take it like as a gospel as to what I'm saying, because you can do this in many ways with various like performance profiles. But in general, it can be done in a single instruction, where you can just do like have a pointer to your table with the addresses in a register, and then you add an offset to it, and then you immediately jump, right? So on AMD64, this is a single instruction. There are also other tricks that you can do, which I haven't mentioned here because again, too long. But you can do fun stuff like AMD64 has those segment registers, and In 64-bit, 2 segment registers are available. So technically, you can use those as extra registers, right? And in Polytechnic, I actually use both. So this nets you 2 free registers that you can use for other purposes, but you need some extra code and some extra complexity because the operating system uses those registers. So it's more complicated to actually use them yourself. So things like that. So for example, for the jump table, I just used one of those segment registers. Yeah.
For the location.
Yeah, for the location of the jump table. Yeah, that makes it like fast, but it's more complex. But you probably don't have to do this again. Like performance-wise, I mean, when we will be like benchmarking all this stuff, you will not be required to like hit 100% as fast as possible because that's unrealistic, right? I mean, we cannot expect everyone to write like pedal to the metal stuff, but as long as you're like fast enough, so you don't have to use every trick in the book, but the more you use, the better. Yeah. Yes.
Yes, so you've been relatively accessible in the gray paper chat room. Do you
Yes.
think it would be useful to have a separate room for this specific topic?
I mean, maybe, I don't know. If you have any questions, I'm always available. I mean, if there will be many questions, then sure. I don't know if there will be, but again, I'm always happy to help and answer your questions if you don't like general questions like this, because this doesn't really do anything with the grade paper. This is just like general, like low-level engineering, right? So I'm always happy to help. And by the way, like if some of you want to chat about this or something, I'm still like I will be here like today, and I think I'm going back on Wednesday, so I'm available until then if any of you want to chat about like stuff. So yeah. Any questions? Good then. Thank you.